Okay, please, I have to ask you that you have to, during now on the weekend, the rest of the time that you have on the week, you please go and review these concepts. You have to learn them very good. I think they're very useful. You can do it also other ways. You can do it also the hard way. You can do it also, and there are some cases where we cannot use this case. But to understand fundamentally what is happening here is very important. It's very simple once you understand it. Okay, so you have to find. I explained to you the way I understand it better. So you have to find yourself the way that you understand it better, and you consolidate. I will also give you some exercise. Actually, the first set of exercise is going to be based on this part. Okay. So we saw that for this case, we said we took a case, okay, some reservoir of certain size that has some pressure decline when you were taking material out, and we said what happens if we produce with this single well all the time at maximum open choke, and we calculate the profile. Then we said what happens if now we want to produce it in a plateau mode, and then we were able to find also to calculate how the Q versus time is going to look like. And we can use this later on to all of our calculations. Production calculations, we can use it for economical calculations, we can use it for the process people that need production profile. Everyone in the oil companies after a production profile. They want to get, this plot is the most important thing for everyone in the company. And even also for us, okay? We're hungry for this data from the oil industry. Okay? So now you know how to generate it roughly. Okay? So the people coming late, they have to sing a song in their language. Okay, so yes, so but this is this case was based on something, we had a field of certain size. We got the plot. I didn't show you how did you get the plot. I will show it later. But was a field of certain size, and from the time scale, you get the impression that if you want to develop this field with only one well, it's not going to be economical. The field is going to last very long, and maybe the rate also, you have that homework. You have to find out if that rate is it a medium rate, small rate, big rate. How is it compared to to a normal field? So we have to find, okay, what is the okay. So we want now to say, okay, what happens if I want to produce more? What can be, according to a rule of thumb, how much I can produce? So the NP I gave you, that value here is 2.7 e to the 11 standard cubic meter, or 270 giga, right? Giga standard cubic meter. The G, that is the initial gas in place, is equal to 2.7 e to the 11 standard cubic meter. So I told you, I gave you a rule of thumb that like a first approximation is good to use, and that is that the plateau rate, Q plateau, is equal to the total recoverable reserves times 0.035 divided by the number of days in a year. So we can say, for example, that we lose 10 days or maybe 5 days of operation, so we say let's put 350, okay, 355. Okay, how much, and how do we calculate? So let's assume we have to assume a recovery factor. What recovery factor for gas do you want to use? Let's say 90%. It sounds okay? Let's say that the recovery factor is equal to 90%. So we get from here that this is 90% times 2.7 e to the 11 times 0.035 divided by 355. So how much is that? Anyone quick with the calculator? With Excel? I have to begin to give some motivation, maybe a point or something in the Excel. 24 million. Okay, that sounds, let's say okay. So 24 e to the 6 standard cubic meter per day. Now we know that one well is able to produce how much? Doesn't reach even to 10 at the beginning. Right? So we have the intuition that if we want to produce 24, we need more than one well. So let's see initially, let's assume, okay, that's something. Then you can play, after you do the calculation and calculate the production profile and calculate the duration of the plateau, you can begin to see what happens if you increase or decrease the number of wells. Okay, but let's say as a first approximation, let's say that number of wells is equal to 8. And that's why, because the reservoir engineer came and told us, you know, if you want to produce 24, so we don't want to produce, average is 3. If you produce more than 3, you will have sand production problems, you have problems there. We have some small water layer at the bottom, but if you pull it, you are taking too much gas out of one well, you might have some coning problems. Okay, or they see all other kind of issues. So they recommend that if we want to produce 24, they say, okay, let's say 3 per each well, maximum. So that gives you a number, total number of 8. And that's only because of reservoir issues. Okay, so we go back and we will say, we will do another assumption, okay? We still don't know where this field is located. Okay, what happens, do you think that if I add 2 wells, 1 and 1 is going to give me the same? It's going to be equal to twice. If I take 1 well to a separator plus 1 well, okay, they are in the same reservoir. So we have to stretch this. Is it going to be the same as 2 times this? What is your intuition telling you? If I have calculated somehow, some guy calculated the production potential of 1 well, right? Okay, so now I say if I want to put 8 wells, can I just make a multiplier? Can I just say that is the production potential times 8? Why not? Huh? Why? Interference, okay, one important word. If there is some kind of competition between the 2 wells, you have the intuition that you won't have the same, it won't be just a multiplier of the production potential. But what about if we assume at this early stage that we are in the US, okay, this is a field in the US, inline in the US, and in the US we can install a separator for each well. In that case, will this be a good approximation? Yes, it's going to be, okay? Because each well behaves in an independent way. Of course, you have to take into account that maybe this well is drilled in a good permeability area, but then you were unlucky that when you drill it here, it's a very maybe compact formation, the permeability is less, so the production potential of that well is less than the other. Okay? But let's say we're at an early stage, we don't know much of the field, but we know that there will be no interference. How do you write interference?
This interference is in the reservoir?
Yeah, that's something very important, a very important question. We are here making the assumption that this is a tank, okay? It has a common reservoir pressure. So really the interference is not there. It's when you have, for example, 2 wells, we will see a bit later, we hope I have time. If when you have 2 wells and they are competing in the same pipeline, when you have this case, you are adding 2 wells together, but they are competing for space in the same pipeline, usually 1 plus 1 is not equal to 2. Okay, because you have interference effect. So we have no interference between the wells in the surface production system. When they are sharing a network, when they are sharing pipeline, when they are sharing, okay, usually here 1 plus 1 is not equal to 2. Okay. I'm going to take that away because I can get kicked out of the NTNU just because, okay, just in case. But when you have sharing, usually it's not the same. Okay, 1 plus 1 is not equal to 2. So let's assume now that we have each one of the wells have its separator. All the wells are identical. The formation is very homogeneous. We were able to complete all the wells in the same way. All the wells are the same and have the same production potential. So how, having the production potential of one well, I can calculate the production potential of the field? I just multiply it times the number of wells, right? So you have QPP of one well versus NP or versus GP. And then if I want to calculate the QPP of the field, I just have to multiply. The GP is going to be exactly the same, okay? Because for every reservoir pressure, I'm going to have, I calculate with that reservoir pressure the flowing potential of one well, and then I just multiply depending on the number of wells that I have. This is equal to 8 times, or I can put it the more generic, number of wells times the QPP of the well. Okay. As at the very early stage, as I told you, to keep that in mind, we're assuming that everything is the same, no interference, nothing. Yeah, and that's usually a good assumption if you are working with early studies. Okay, so we go back to our sheet, Excel sheet. So now we say, what is the field production? Okay, here I didn't wrote it, but we said it's 24 e to the 6. Okay, using rule of thumb, we can reduce 24 million, and we say that we have 8 wells. Again, I have already created a column here for you that is calculating based on the potential of one well, production potential, calculate the potential of the whole field. So now let's calculate for this system what happens if I don't choke. Okay, if I'm not control the rate to 24, if I don't choke. So for that, what do we have to do? We have to come back to our example, and then now instead of taking the production potential of one of the single well, you have to take it from the field. So I just drag it here. God bless Bill Gates. We just click enter. Okay, and you see I'm able to reach the same cumulative production, but now in much less years. Why? Because I'm just producing for many wells at the same time. And now it looks more reasonable. Now it says that if I produce maximum, I just leave the choke open and produce everything that I want, it will be finished in 18 years. That sounds more reasonable. That sounds more like a real system. Now let's go to plateau production mode. What was our rate? 24, right? So when do we get 24 in this production potential? Let's change here well, we can just create a new one. And we can say QPP of the field versus GP. And here we have to select I think is D, right? The column. Okay. So where do I get 24? 24, I get it someplace here. So it's exactly at this, close to 1.5 e to the 11. So I go to my table. Where do I have 24? Here we can say that's 235. That's a okay rate. So I'm able to keep the plateau up to this point. Okay, so I just come here and say plateau production is 24 e to the 6, and all the way to, where do I have it? That one. Okay, one down. Okay, I'm able to produce up to that point, and from there on, the time is going to be calculated as yeah, this is not the well potential, but this is the field potential. Okay. problem here. Oh, this should be. Oh, this should be the field, right? This should be D. Okay. So you see exactly what the intuition told you, but now it's with numbers. Now it's with proof. Okay, so if we produce just open choke everything, you obtain 80, and you have to find out if that's remember, you have to find out if that's a high rate or a small rate. Or if you produce, for example, you go to a person and you say, I can offer you, 24 million standard cubic meter per day of gas, then you will be able to produce up to almost 20 years, 18. And then you will enter into decline. So you can tell them, I can offer you 24 for 18 years. What happens if I want now, it says, well, I like your proposal, but I need 30 years. What will you do then?
Lower down the plateau?
No, the same rate. They say, I need 24. That's what I need to produce power for this community. Otherwise, they're going to make a rebellion because I don't give them electricity. But now I need it for 30 years. Can you do it? What can you do? The one way will be you cannot change the size of the reservoir. You can we will see later, we can put some EOR that we can say we can increase or support that the pressure would not go so abrupt with MP. But one way to do it will be just right away is to increase the number of wells. If you put, for example, 10 wells. Okay, try it at home. I won't do it here because I want to cover something else. Is that clear? Yeah. So for example, here, if you increase the number of wells, you will see that the production potential curve would also increase. So that means that you will be able to produce for a bit longer. And you have to see if that pays. For example, if you put 2 more wells and you get maybe 5 years, you say, okay, that's a good saving. I will have to put only 4 wells. But if to put 2, you only reach 1.5 years more, you see already that that's not an economical alternative because you have to put a lot of wells and the cost of your field will be so high that it doesn't pay the investment. Okay, so let's take that. I use the same exercise, so this is the one that I'm going to post because I'm replacing all the values. So you have to create it or save it like a separate version for the well. Okay, single well case. 24. Okay, so that's D and E. Okay, so now we are done with this topic, and you're going to have an exercise, and probably we're going to have a session, or if you need to discuss the exercise. If you see that you have too many doubts, then we can take another session too. The exercise is going to have one like that you have to see the effect of the number of wells, and you have to plan your field, and you see if you are able to deliver the plateau that you need. And the other exercise is going to be with 2 fields. What happens when you have 2 fields? And then you have to put some good thinking. Okay, so now let's make a break of this topic. Before we go, any question? Suggestion? No? You're quiet. You want to go home. So now let's talk a bit about the architecture of production system. You saw already that it has some effect on all of these calculations of rate profile and production profile. It has a lot of effect, the production system. How is my well, or how much it can produce. So I'm going to discuss a bit about that. So in the traditional way, wells, they can be, if you have let's put it like a dot. Okay. Wells can go either to 2 ways. One of them, if we say we have, let's say, 2 or 3 wells, they have the facility to go to the main production separator, or they can be also taken to a test separator. So why do I want to have two separators? Why I want to invest a lot of time and money to have two, you see here, two pipelines, two transport lines. Why do I want to invest all of this effort to have a test separator? What do you, can you think why we want to have a test separator? Two? Sorry? Measure the rate. Okay, so why do we want to measure the rate? Now, I go into your suggestion.
Because you want to see the potential, how much a well can produce.
That's one thing. What other?
The type of fluids flowing by.
Okay, so let's put here. So you want to check test separator. The test separator is used to measure rate, okay, and the rate we measure it to maybe check the fluid behavior. We want to know what else, to check the potential of the well. Okay, what else can it be?
Water cuts.
To measure water cut, that will be inside fluid properties. Yep.
Also, we usually have the limited, for example, gas and water handling capacity, so that we can plan accordingly.
Okay, so detect which wells are producing with high GOR. Detect bad wells, we can call them bad wells, or with high GOR, gas oil ratio, or high water cut. Okay, this stands for gas oil ratio and water cut. You're going to remember, or I should write it? Okay, one thing that is important and every reservoir engineer is looking after that is data to match their models. Okay, they want to see they have a computational model and they want to see to have it as accurate as possible to the reality. And this data is very important to see how much is actually the well produced. Match reservoir model. Okay, to tune and match the reservoir model, there is one more that they want to see if they're actually the recovery strategies is proceeding properly. Maybe they're getting too less from one well and they will leave one area behind without any development, so they want to detect that very quickly. So that will be verify reservoir recovery. But we are missing the most important cause, the most important objective.
Economics.
Sorry, economic.
Yeah.
Okay, so why is that?
So to see how much money we can earn.
Exactly, to cut the cake. Okay, that's the last point, to cut the cake. If the well, usually the wells are not produced only by one people. There is a lot of people involved in that. Okay, and they want to see how much corresponds. Let's say that well 1 is from Statoil, well 2 is from ConocoPhillips, well 3, and all of them are producing to the same system. So how, from all the money that is coming here, that is making everyone happy, how to split the cake? Okay. And we might be a bit naive to say, okay, we need it for this, for that, behavior, performance, that's okay. But at the end, what convinces the management is say, from this money that you're getting here, that's how you're finding out how much each one is. So don't be a naive. It's a lot of things, and we like to have them, and we like to argue about it. But the main thing is to cut the cake, okay? To split the cake. And that in engineering terms, in petroleum engineering terms, is called allocation. To determine how much is coming from where. So that's the main justification to have a test separator. So how do we make the well to go from one separator or the other? We want to be producing normally to the main production separator. So how do we divert the flow?
You should have like an extra pipeline.
Okay, we have this extra pipeline, this is called test line, and we have the production line. But how do we route the production of the wells to one or the other?
On the choke.
With a choke, are you sure? The choke is something that I regulate. Remember the choke, what happens, maybe you get the impression, what happens if you are choking, let's say in that case that I have here, okay? That I showed you. Okay, what happens if I'm choking? I'm all the time causing a very important pressure drop. Okay, because that's what that guy is doing, is losing energy. So what's going to happen, do you think, at the end with the choke? Is it going to last long? Why? Because it has a lot of erosion. When you have a lot of losses, you have a lot of the fluid velocities are high, it's causing a lot of erosion, a lot of wear in the choke. Okay, so you don't want to use the choke to close, because maybe when you close, it won't close at all, because all the seal surfaces are just worn. Okay, so we don't use a choke to divert flow.
In the Christmas tree, there is.
We use some valves, okay? Open or close valves. Some valves that I'm only using to open and close. Only for that. I don't use them for control. So there is a big difference between control valves that such as chokes, okay, or those used in the chemical, and these are on and off valves. This I have to be sure, if I close the well and something is happening, a fire, something, any other place, I have to be sure that when I close that valve, I'm not going to get any hydrocarbon. Has to be bulletproof. And I cannot take a chance to use the choke for that. Because the choke, because of the use, the way it is used, is not made or is not going to seal properly. So those valves, I'm going to put them like that. And these valves, I'm going to use this symbol, or I'm going to use maybe also this symbol. Okay, with a line in between. So for that I'm going to put, in order to divert, I'm going to use the following. So when all of them are, let's say I want to put, let's put names to the wells, well 1, well 2, and well 3. Okay, let's say I want to put 1 to the test, I want to see how much it is producing, and all the other 2 to production. So how the valves should be? This one should be closed, this one should be open, and this one should be closed, and this one should be open. Right? Now when I want to change, put 2, then I close here and I open this valve, and then again I close this valve and I open this valve. Right? Okay, now I'd like you to do some work. Now that you have seen this, what happens if we have 3 wells? So this is a class exercise just to wake you up. We have 3 wells, and we have now, because sometimes only one separator is not enough, it doesn't have enough capacity, so I have to have a train of parallel separators that will take my production. Because of size, space, I cannot make just a big separator, and maybe it's not very efficient, so I prefer to do small separators, in this case 2. So we have separator A, separator B, and test separator. So I want you to make now, just grab a pen and tell me how do you connect, to have the option to connect each well to separator either A, B, or test separately. Okay, go on and work and do very quickly in a piece of paper, and just how it will look like. The question. I showed you now how to connect all the wells, okay, to either separator or test separator. I want now, if you have another system where you have 2 main separators and the test, You please show me what arrangement of valves I have to have here in the middle to allow me to route either to A or either to B or either to the test. Okay?
One well will be connected to one separator. We are not dealing with multi-state separation.
No, only one.
Där stannar jag. Jag ska kunna måla allesammans. Ser det bra ut? Får vi ut det där? Så du menar att du bara den? Ja, den bara den som kan vara så bra och bäst. Du kan bara få det. Jag gör också nog han. Så den kan gå till vatten. Det kan inte alla. Den hamnar.
Okay, so I have done the homework for you, but it's very important in these small exercises. You shouldn't say, okay, something that this guy, is just trying to, we are not kids. But really, that's when you see a process and instrumentation diagram, sometimes it's difficult to find out what's happening because you have so many connections and it's difficult to find the way the fluid is moving. That's something that you need, for example, to do production calculations, to do any other kind of calculations. So you have to be very clear and follow and be, you know, have a smart engineering assessment of how is your system. So in this case, I have done it flat. Okay, so you have from well 1, you have it has 3 lines. One of them is going to the test separator, and I'm going to put a point. The point is indicating that there is actually, you know, might be a welding, might be a derivation from the line. Okay, and this valve allows it to go to the test separator. This valve allows it to go to the separator B, and this one to the separator A. Okay, and the same thing with well 2. This valve to test, this to A, and no, this one to B, this one to A, and that one to test, and so forth. If you see it maybe in a more kind of engineering way, that's how, and I will show you very soon how some manifolds look like in real life. Okay, that's how it will look like. Now I will show you some examples, some images. Okay, like let's start with fields, onshore fields. There is a bit easier to see. So you have, let me copy that. These are the wells. This is what is called a pad. This field is, let me just put you the picture. This is a picture from the Rubiales field. It's in the Llanos in Colombia. Okay, the area looks like that. So they have to, in order to install the wells, they have actually to cut the trees, okay, or they have to take away of the vegetation. They have to be careful with snakes and also narcs and any kind of things, animals that are on the forest. And then they make this nice pad and they drill these 4 wells. And you see each well has, maybe put it bigger, okay, each well has a line that is going underground because here there are trucks that are passing. And then if you see how the manifold looks like, where I had it, okay, that's how the manifold looks like. In that case, the crude that they are producing doesn't have much gas, and they don't do the separation here, but they take it further with transportation lines all the way to some production facility. But they want to know still how much each well is producing, okay, to know, to do all of these things that we mentioned before. So here you see at the bottom, you see all the pipes coming in, okay? And each pipe has, you see the 2 valves here. You see the each well has a line going up that takes it to the main production separator, or has another line going up that takes it to the test separator or test header. Okay, and all the wells are normally on this header, and they are just pushed to production through this big line that you see here at the bottom. Okay, but when you want to test one well and you want to see how much is passing through it, you just close this valve. Okay, each one of the wells has its own valve. So you close the production header valve and you open the test header valve, and it will go to this header, and then we'll go to this line. There is a flow meter here. You see this small blue thing that flows the fluid from the test to the production, and that's how they know how much each well is producing. Okay, let me see if I have a better picture.
But we can also use the mobile separators.
Yeah. Okay, so that's one specific case. We don't need to have a separator. No need for separator. Just a production. Production header, production manifold, and test manifold. and that's because it's single phase oil and water, and because I can measure, that's actually that's a Coriolis meter. Okay. A very particular case. Now there are some other cases where we have the test separator is fixed, and that's typical in this kind of installations offshore. Okay, let me take another picture if I can find it. Okay, this type of there are some, for example, some mature fields in the North Sea that are using this concept, that they put a platform. It can be a concrete platform, it can be a steel jacket, it can be any type of platform that you want, and they put all the wells, they drill them from the top, from the platform floor. Okay, so you see from here all of these small conduits, they are all of the wells that are being drilled from that platform. So then they have the wellhead just in the platform. So what's the advantage of having the wellhead in the platform compared to having it subsea? Okay, let me show you a picture. That's how a subsea Christmas tree looks like, and that's how a surface Christmas tree looks like. Which one do you think is more expensive?
Subsea.
Okay, subsea for sure. So one motivation for doing that is that the cost of the tree is less. The cost of the tree. Now, what is the drawback of this case? You have to go all the way through the sea sheet, through the water sheet, okay? And the well has to be, all the wells are departing more or less from the same place. But if they want to reach different places in the reservoir, they have to be highly deviated, horizontal, and they have to have a very difficult structure. So they might be more costly because of that. Okay? When you have it, the wellhead subsea, not all of them have to be on the platform, but you can drill exactly, if you have one area of interest, you can drill exactly over that. Yeah, and the well doesn't have to be too complicated. No. But that was not the story. The story was that in that case, all the wellheads go up and they are available at the platform. So in that case, I'm going to show you a picture I took from a brochure. We're going to have to zoom in maybe. Okay, and you see here the primary inlet separator and the secondary inlet separator and the test separator. When you have all the wells there, it's very simple. If you want to test the rate, you just put it to the test separator, and in the platform you have to have all the separators. What to have two here? Because probably it's not enough with only one, but I told you the size is limited, so that's why they put two parallel. And for the well, you see the production well has the option either to go to the inlet separator, the first one, has the option to go to the secondary, or has the option to be put to test. And in this case, like you said, the test separator is a permanent separator that stands in the platform. It's not a portable separator. Now, what he was mentioning is something very important. When you have land installations, maybe there is very costly to put a test separator. Let's say that they are spread, okay? So you have a cluster of wells here, and you have another cluster of wells here, and you have another cluster of wells here, and at the end you gather the production of all of them and you send it to the main processing facilities. Okay. But it might be very costly for each group of wells, like in that case, to make a separation for each one of them and to have a permanent separator there. So what is done is that, I'm going to show you another picture. Okay, that's a test separator. That's how they move it from place to place. Okay, it's not a small thing. You think it's a very small tank, but it has a lot of things, equipment and things installed. And after you place it in, it doesn't come with the truck. Usually they leave it there in the place, so it looks like that. That's called a skid. The test separator is located on a skid. Okay. And in the cluster itself, where you have the group of wells, you have this arrangement. and you already know, and you can sketch, and you can know exactly what what is doing each valve. But each well can go, this earth from the well can go either to the test line, to the test manifold, to the test header, or can go to the main production header, that is this one here, that you saw already how it looks like in reality. And if you push them, all of them, through the production line, it's just going to follow the main pipeline and go directly to the processing facilities. But if you want to measure how much that well is producing, you just put it to the test line, and here you connect the test separator. And it might happen that you don't have the separator, so that's just empty. Okay? They're just a blank spot. When you bring the separator, you put it there, you make the connections, and with that you plan to test the wells for some period. Then you take it out from there and you go to another cluster and you measure. Okay? Let me see if I have one more picture. Not on that issue. Okay, here I have another test. This is in a field in Libya. So you have a test header and a production header. The same arrangement. The wells can go either to one header or through the other, and they have the valve where you can regulate. Open this one so it will be to production, or open this one and it will be to the test. Okay, I think we have covered what I had for today. Just to make a brief summary, we looked a bit more in detail about what is this very useful concept that is production potential, okay, and how it depends on the reservoir pressure, and also we can say that it depends on the cumulative production, and we have this relationship is very powerful. We had some intuitive idea that if the plateau is longer, okay, we will be able, and the rate is small, we can produce for longer, but if the rate is higher, then we can produce for a short time. This particular example allows us to calculate, actually to do estimation. What we have to do now is to see where are these plots coming from, okay, where should we ask, or if we want to generate by ourselves, how can we do it? Also, one thing that I didn't comment was that we are working here with the points, a collection of points, because it's a bit more general. That's usually what the people from reservoir and production are going to give you. But also what you could do if you're good, you have some good mathematical skills that you want to use, you can tune this curve to an equation. In one of them is just a straight line, and you can do the integration analytically. Yeah? Just try that. Those of you who are curious, try that, and you will get exactly the same thing. So we saw that part, and we will have an exercise to practice that, and then we began to see, I didn't go too much in depth, but we began to see about the production system that we have. Usually we have the option to divert the flow either to a main production separators, through a main production header or main production manifold, or to a test separator, and we saw also why it's important to test the well. Right? Any question before we close? Okay, see you next Monday.